we have Samantha. Yeah, so next up we have Samantha Moore from UNC Chapel Hill. And you're going to connect for us Bigraded Betti numbers to generalized persistence diagrams.
Yes, all right. So thank you for that intro. So yeah, today I'm talking about how the generalized persistence diagram determines the Bigraded Betti numbers. And this is joint work being done with Woojin Kim over at Duke University, who is also here today. Hi, Woojin. All right, so let's see. So some background first, just sort of general persistence vocab that you've probably heard a lot today, but we're going to go over it again. So first of all, persistence module, the way that I think about it is we start with some directed acyclic graph, and then to each of the, sorry, not sure why it's making that noise, to each of the vertices we're going to attach some vector space, and to each of the edges we attach a linear map so that the resulting diagram commutes. So for example, going from here to here, I have two paths. I have the path along the identity map, and the path that takes the inclusion map to the first axis, and the projection map from the first axis. So I need those compositions to be equal. And they are. So this is a persistence module. And a very common underlying directed acyclic graph that we're going to see is n to the n, where it's given sort of directed acyclic graph structure as follows. So n1 is given this directed acyclic graph structure. So we're going to put a vertex at each point of n, and then we're going to put edges going from x to x plus 1. N2, similar idea, put vertices at each point of n2, and then put edges from each xy to x plus 1y and to x y plus 1. So every time you increase one coordinate by 1, you're going to put an edge, and that's what you do in general for n to the n to give it a directed acyclic graph structure. Okay, so I won't go into details too much, but why do we care about persistence modules? You've probably seen sort of more detailed explanations of parts to this, but I sort of think of the full persistence pipeline. First thing you're going to do is you're going to start with some large data set. And then based on information within that data set, things like distance between points, density of points, yada yada, you're going to build up a set of related topological spaces. And you're going to have some inclusion maps between these. And so you can apply homology and end up with a persistence module. And then you can study things about the persistence module, its properties, its structure, its invariants, and that sort of information can be pulled back to say something about the shape of those topological spaces, which can then say something about the shape of the data set. My work almost entirely lies in this arrow. I really like avoiding data, apparently. So you're going to hear a lot about this arrow today. Okay. So given two persistence modules, we can compute their direct sum, and this is very much just done pointwise. So for example, if I want to take the direct sum of this module with this module, you can see my cursor, right? I should have asked that earlier. Perfect. Okay, so if I want to take the direct sum of this module with this module, then I just do it pointwise. So for example, I'll take r cubed direct sum r squared, so I'll get r to the 5 here, and so forth. And similar with the maps. So I'll take the identity map on the first component. Oh, sorry. So this map is given by the identity map on the first component to the first component, direct sum with the inclusion map from the first component, or sorry, second component to second and third components here. So very much just pointwise direct summing the vector spaces and direct summing the maps. We say that a persistence module is indecomposable if whenever I write it as a direct sum, one of the summands has to be the zero module. So 0 vector spaces everywhere and 0 maps everywhere. So essentially, indecomposable modules are the ones that can't be broken down any further using direct sums. This plays really nicely with the Kroll-Schmidt-Remak theorem, which says that if we're starting with a finite persistence module, so finite vector spaces and finite support, then we can write that module as a direct sum of indecomposable modules. And indecomposable modules can't be broken down any further via direct sum, so we have basically our indecomposable modules are going to be our building blocks for all persistence modules. a little bit more vocab and then we'll get to our invariants. So a connected set is essentially a set that's going to have one connected component. So each of these sets have one connected component, each of these green sets. So these are all connected. And then these sets are examples of not connected sets because they have multiple connected components. Once you have a connected set, you can ask whether or not it's an interval. And for it to be an interval, you need that whenever points P and Q are in your connected set, any path from P to Q is also in your set. So for example, this point P and this point Q being in my connected set, if it's an interval, because I also have this path from P to Q, then I would need this point and this point to also be in my interval. So for N2 modules, they all have a backward staircase sort of shape that you can kind of see with these. So the idea is if I want to think about like walking from right to left along my module, it's vaguely staircase shaped in each of these. That's true for any interval in N2. So then once you have an interval, you can create an interval persistence module. So the idea is within my interval, I'm going to put just a copy of the one-dimensional vector space. So I'm going to put R within my interval, and then outside of my interval, I'm going to put the 0 vector space. And then the maps within my interval are all identity maps, so all these green edges are identity maps. And outside of the interval, of course, all of my maps are the 0 map. So this is an interval module with support the green interval. Okay, with that, we can finally start defining some of our invariants. So the rank invariant of M on a connected set J is going to be a number determined as follows. So you're going to give me a module M and some connected set J. So my connected set is this green one here. To determine the rank of M at J, I'm going to first restrict M to J, so delete everything else. And then I'm going to take that module and I'm going to calculate its indecomposable decomposition. And so rank of M at J is going to be equal to the number of full support interval modules. So in the indecomposition. So I see one full support interval module once I've calculated the indecomposable decomposition. So I say that the rank of M on this set J is 1. So that is the rank value. Take a module, take a connected set, restrict down, calculate the indecomposable decomposition, calculate how many full support intervals you see, interval modules. So we can use the rank invariant to calculate the generalized persistence diagram, which is going to be a sort of alternating sum of these rank values on nearby sets. So the generalized persistence diagram of M at J is going to be an alternating sum of rank values on connected sets near J. I think this is clearest in an example. So if I want to calculate the diagram value of M on this connected set J, then the first thing I need to pay attention to is where are my neighboring points. So this vertex, and this vertex are all one edge away from my connected set. So these are my neighboring points. And so I'm going to have an alternating sum of rank values based on sort of the adding in those neighboring points. So first I'll take the rank value of M on just my original connected set. Then I'm going to start adding in one point at a time, and I'll change my sign. So I'll subtract off the rank value of M on the original connected set union this neighboring point. Subtract off the rank value of M on the connected set union this neighboring point. Subtract off the rank value of M on the connected set union this neighboring point. Now I've ran out of 1 point things to add in, so I start adding in 2 points and I change my sign again. So now I'm adding on the rank value of M on the connected set union these 2 points. Adding on the rank value of M on these adding on the rank value of M at the original set union these 2 neighboring points, and then rank value of M on the original set union these 2 points. I ran out of 2 point sets, so I'll add in all 3, and again change the sign, so I'll subtract off the rank value of M on the original set union those full 3 neighboring points. So it's just going to be the generalized persistence diagram of M on a connected set is just an alternating sum of rank values on sort of nearby sets based on how many added in neighboring points you've added in. So at the end of the day, what the diagram does is it gives me for every connected set J, it's going to spit out an integer. And there are a number of reasons to care about the generalized persistence diagram. One reason for me that I really like is that it's a generalization of the notion of barcode. So in particular, if your module M has a direct sum of interval modules, then the generalized persistence diagram is very nice. So for example, this module can be written as the direct sum of the full support interval module plus the interval module with just this being its support, plus 2 copies of the interval module with this support. So just looking at this without calculating any rank values or anything like that, I can say that the generalized persistence diagram value on the connected set J, which is the full support, will be 1, because I have one interval module with full support. The generalized persistence diagram value of M on just this connected set, just this point, will be 1, because I have one interval module with that support. Diagram value of M on this connected set will be 2, because I have 2 of that interval module. And then for any other connected set that you can point out, the diagram value will be 0. So diagram values very much generalize the notion of generalize the notion of interval decompositions. Another reason that I didn't write down is that, as I believe was talked about just before this, generalized persistence diagram is a Mobius inversion of the rank invariant. Those are going to be equivalent invariants. So we'll see how that comes into play later. Okay. So those are 2 of our invariants. And then the last one is the Bigraded Betti numbers. Of course, if you've seen sort of the free resolution version, that is exactly what this is. I decided to talk about it today in terms of generators and relations. So for a given module, we can talk about generators and relations. Okay, so for example, if we take the basis vector in each of these copies of R, then those will generate the full module. And in fact, this is a minimal generating set. So then we can talk about relations. Those are going to occur where any linear combination of our generators are mapping to 0. So for example, V maps to 0 when I apply M's map going this way. So V maps to 0 here, so we have a relation here. W maps to 0 here, so we have a relation here. And then going into 1, 1, both V and W will map to the basis element 1, 1. So V minus W is going to map to 0 when we go into 1, 1. Then we can do a similar thing looking at sort of relations between these relations. So this was V mapping to 0, this is W mapping to 0, and this is V minus W mapping to 0. So when we get here, we see that this relation minus this relation equals this relation. So we have a relation between relations occurring at 2, 2. So those are the sorts of things that the Betti numbers pay attention to. So the bigraded Betti numbers of M at a point P in N2 are given as follows. So the 0th Betti number of M at your point P is just how many generators there are for M at P. But the first Betti number of M at P is the number of relations of M at that point P. And the second Betti number of M at P is the number of relations between relations that occur at P. So in this example, sorry, I think it's just taking a little bit longer than usual to flip between slides. Okay, anyway, so in this example, I'll have Betti 0 being 1 here and here because I have one generator at each of those places. And Betti 0 will be 0 elsewhere because I don't have generators elsewhere. Then Betti 1 will be 1 at each of these sort of squared locations because I have one relation at each of those places. And then Betti 1 will be 0 elsewhere because I have no other relations. And then Betti 2 will be 1 here because I have one relation between relations. And it'll be 0 elsewhere because I have no other relations between relations. So it keeps track, the Bigraded Betti numbers keep track of where and how many of these generators relations and relations between relations that we have. Okay, so summary of the invariants so far, because I know I've thrown a lot of examples at you. So rank of M at J, you're going to give me a module M, you're going to give me a connected set. I'm going to look at M restricted to that connected set, calculate the indecomposable decomposition, and calculate how and look at how many full support interval modules I have. Diagram of M on a connected set. I'm going to do a bunch of alternating rank values of sort of nearby sets, and I'm going to get an integer out. And then Bigraded Betti numbers keeps track of where our generators' relations and relations between relations are. And with that said, there we go. So this is our theorem with me and Mujin, and we said that if you have a finite N2 persistence module, so again, finite support and finite dimensional vector spaces, then the generalized persistence diagram determines the Bigraded Betti numbers. In particular, we do have a formula for this. It is a bit complicated, but we have a direct formula for this. So the Bigraded Betti numbers of M at P can be written as a direct sum of diagram values on connected sets J, where we're going to sum over J or not based on essentially just which points are in J, looking at the point P minus 1 in each of its coordinates, and then P minus 1 in both of its coordinates. Like, that's all that I need to pay attention to, the connected set. And just sort of looking at those points, which of those are in the connected set will determine whether or not I'm summing over it in each of these summons. So yeah, full formula for how the Bigraded Betti numbers come from the diagram value. And so idea of the proof is that this is well known in commutative algebra, which is that the Bigraded Betti numbers can be written in terms of some other sort of nice simple invariants. So the dimension vector of M at some points, and then so this NP and M sub P minus E1 minus E2. Didn't want to get into it too much, but this is essentially, it comes down to a you can determine this by looking at the decomposition of very small zigzag modules within your module. So very easy to compute invariant. And so, yeah, the Bigraded Betti numbers can be determined this way. And so it comes down to showing that the generalized persistence diagram determines each of these summons. But as I said earlier, the generalized persistence diagram is equivalent to the rank invariant. So really, we can show that the rank invariant determines each of these summons, and that comes down to an inclusion-exclusion argument. So that is quite straightforward. Okay. And with that, citations, and thank you.
Thank you, Samantha. Do we have questions? Yeah, we do. Or maybe not. So maybe I have a question, Samantha. I spent a lot of time looking at these Bigraded Betti numbers as free resolution, seeing if they'd be helpful for actually computing the generalized persistence diagrams. Have you seen any indication that the Bigraded Betti numbers might actually help in computation, useful in computation?
See, funny you should mention that. That's kind of exactly what we wanted. We wanted, see, the opposite of this. We wanted, yeah, the diagram equals something in terms of the Bigraded Betti numbers. And so, no, we have not gotten that yet.
Okay.
This is what we found instead, was the exact opposite, sadly.
Because from
Yeah.
the examples I've been playing with, it seems like the Bigraded Betti numbers encodes exactly where the births and deaths are happening, but it's not clear exactly, like, yeah, I can't figure it out. There seems to be something there.
Yeah, that was, yeah, exactly our hope, and this is what we've gotten so far. Yeah, that was our temptation too.
Sorry, maybe can I ask a related question? And maybe this is, you said this, but maybe I missed it. Do you have examples in which the bigraded Betti numbers of two modules are the same, but the generalized rank invariant or the generalized persistence diagram is different?
Oh goodness, it's been a little while since I've been staring at our examples. Wujin, do you remember if we have that? We've got a lot of weird counterexamples of things, so I'm almost certain we've got it lying around, but I'm not sure off the top of my head.
So the same generalized rank invariant, same generalized persistence diagram, but different, not
Vice
non-isomorphic
versa.
modules. Right.
Different Betti
Yeah,
numbers.
they're yeah, different Betti numbers. Yes,
No,
there
so
should.
I was asking same Betti numbers, but different generalized persistence diagram.
Oh, sorry. I don't even know what question was asked.
Okay.
Like, because this is basically asking, can you recover the generalized persistence diagram from the Betti numbers?
Mm-hmm.
And if there's such an example, then you can't.
Right.
Oh, right, yeah. I would want to
I don't
say
remember.
yes, but we'll have to. We've got a bunch of counterexamples written up. We can certainly try to find that. And then was Amit who asked that earlier? We can send you an email if we find that example written
Okay,
up.
yeah, that'd be very useful.
Yeah.
I'll be interested too.
Thank you. Yeah. Could you both put your email in the chat and I'll just screenshot it so I remember who I'm emailing. Thank you.
Thank you.
Perfect. Thank you. Put in the chat what I'm trying to find. So same Betti numbers, different GPT. Okay. If I don't have it written down, it didn't happen. So now it happened. Now that email can occur. Okay. Any other questions?
Okay, what time? Let's see. 10:20.
I think there's 8 more minutes in my time slot,
Oh,
technically.
you did end early. Okay.
I did end early, yes.
I got confused.
Yeah, Samantha, do
Yes.
you know if there's a way to view the multigraded Betti numbers as a Mobius inversion? It seems like there should be a way to do that.
I do not know. I'm going to be very honest. This is my first foray into category theory. Wujin is the one who has taught me all of the category theory for this project, and that is why the slides did not involve any category theory, because I did not want to lie to anyone. So yeah, I don't know the answer to that.
So I have a partial answer to that. The Hilbert function is the Mobius inversion of the multigraded Betti numbers. You can recover the Hilbert function from the multigraded Betti numbers. You cannot go back because the multigraded Betti numbers are going to cancel things.
Yeah.
When you go to the Hilbert function, but there is one implication. If you know the multigraded Betti numbers, you can get the Hilbert function, and you do that by Mobius inversion.
I see. And so you're going to talk about this later, Luis?
I'm going to mention it in the end. Yeah, yes.
Yeah, I think to prove that, it kind of comes down to actually playing with this, because you can see if you subtract off the second bigraded Betti number and the first bigraded Betti number, then you get just a bunch of the dimension vectors if you subtract that from the first bigraded Betti number. So I think what he's saying comes down to some manipulations of this formula, actually. Yeah.
Okay. Yeah.
Okay, so we have a few more minutes till tomorrow.
Cool. I will stop sharing.